So we talked about the fact that when you bring charge into some space, that what that does is it sets up an electric field. And that electric field is a vector field, which means you can go to any point P you want, say this particular point P right here as an example, and there will be a vector that corresponds to the electric field at point P. And so like any of these vectors, right, you pick a different P, you get a different vector. You pick a different P over here, you get a different vector. What all of these vectors are telling you is they've got to tell you two pieces of information. They've got to tell you the magnitude of the electric field, and they've got to tell you its direction. So we could represent the electric field sort of through space by simply drawing a whole series of vectors all over the place. So basically we could literally draw out the vector field much like I've done right here. An alternative way of showing the vector field is going to be to use vector field lines. But vector field lines have to give us the same pieces of information. So let's be clear about how the vector, how drawing out all the vectors give us the information. Well, again, one, they tell us the direction, right? You draw in the vector, it shows you the direction at any point P. And then the longer the magnitude of the vector, the stronger the electric field. So here, where you're in close to the charge, right, these are all electric field vectors that are strong because they're much larger in magnitude than what they are over here where the field is weak and you have much shorter vectors. So this is how, using vectors, we represent the two important pieces of information about the electric field, magnitude and direction. If we want to use electric field lines, we've got to have those same two pieces of information. And so there are some rules that we have for doing that. So the rules that we're going to use for the electric field lines. So the first one is, at any point, basically the field line has to tell you the direction. So if the field line is straight, it points in the direction of the electric field. If the field line is curved, then the tangent to that curve at the point you're interested in tells you the direction of the electric field. So one of the important things about field lines is that they will also have arrowheads the same way our vectors do, because they have to show us directions. So they can't just be lines, but they have to be lines with a direction. Two, when we draw field lines, we also have to indicate the magnitude, and the way we do that is basically by how compressed or spread out the field lines are. So the way you sort of think about magnitude in a field line diagram is to think about how clumped together are the field lines. If the field line, in regions where the field lines are relatively clumped together, that's places where the field is strong. Where the field lines aren't clumped together at all, that's a region where the field line is weak. And so how close together or far apart the field lines are is indicating the magnitude of the electric field. And then again, thinking back to direction, we know that electric field lines will extend away from positive charges, so they'll point away from positive charge just like our vectors did in the previous diagram, and they'll point towards negative charges. So oftentimes when we draw electric field lines, they'll originate from positive charges and terminate on negative charges. Alright, so let's come back to our example here. So here's the vector diagram showing the vector field. And all we're going to do is just turn it into exactly the same diagram, but with field lines. And so what you'll see is, instead of drawing a whole bunch of individual vectors, what I'm now drawing are lines. These lines all have a direction, so they're telling me again that pick any particular point you want, and the field points away from that positive charge. Here, in close to the charge, the field lines are relatively close together. When you get far away, they're much more spread out. So again, this is telling you that the field is strong and close to the charge, and it's weak as you go further away from the charge. Now again, this is a representation, and in the same way that our picture before didn't have a vector for every single possible point P, we don't have a field line for going through every single possible point P. So just because, say, this point right here, where my cursor is now, there doesn't have a field line through it, doesn't mean that we're not sort of getting information about the electric field here. So there is still an electric field at this point, whether a field line runs through it or not, there is still an electric field. At this particular point, again, basically what we would do is we would interpret, oh, so what's happening is all of these lines are pointing away, so I would expect that since my lines point radially away, it should point radially away at every point, so the electric field should point radially away from my charge here. And then again, I'm getting into a region where the strength of that electric field is weaker than what it was when you were in closer to the charge. So we may often have to, for some particular point P that doesn't lie exactly along the field line, we may have to interpret what's going on from the field lines at that point. So this is the representation that we'll often use to show the electric field. So here are just two examples, right? So here is the electric field due to two similar charges. And again, so this is a positive charge and a positive charge. So part of what you can see is there is a region in here where the electric field is incredibly weak, and in fact at the point right here in between the two charges, it's actually zero. But here is a region of weak electric field because I don't have any lines. Again, here, when I'm close to my two charges, I've got a fairly strong field. My lines are fairly compact through here. You notice when you get sort of along the edge over here, my electric field, these lines basically all run parallel, roughly speaking, through the middle here. This tells me that my field is roughly uniform when I get sort of far enough away along the axis splitting these two charges. So here I have a roughly uniform field, and that seems to be true on both sides. Again, as I get farther away on the back sides, I notice that my lines are getting farther and farther apart, so I must have a weaker field over here than what I have as I get in closer. Second example is if I have two charges that are the opposite charge. So these are what are known as an electric dipole. So I got a positive charge and I got a negative charge. And again, what you see is now instead of the field being weak in the middle, it's actually very strong. So the strongest field when I have two opposite charges comes right here in between them in the middle. And then as you go farther and farther away, again here on the edges, the field is clearly much, much weaker because things are getting much, much more spread out. So the other piece of information that I have in all of these is, again, the direction of the field. And you notice that in this picture, the field lines all start from positive charge and point away. So they all originate on positive charge and they all point away. Originate on positive charge but all point away. Here with my dipole, they originate from this charge pointing away, but they point towards my negative charge. So here you have, up here, all these field lines are running away from my positive charge. All these field lines down here are running towards my negative charge. And in between, same thing's happening. All these field lines run from my positive to my negative charge. So these are sort of the rules that we'll use both in drawing and in interpreting field line diagrams.